All right, so we have our Chapter 6 review happening here. This is going to be in the format of a PowerPoint. This is the same as our review sheet that we passed out this week, but thought it might be useful for us to get an actual video of the problems getting done, albeit gone through pretty quickly. First one there, 30 Newton force is applied across some distance of 13 meters. How much work was done? Okay, so pretty straightforward problem. Work is equal to F times D. That's our basic equation for work. They're both going in the same direction, so nothing funny going on. So 30 newtons, just write that again. 30 newtons times 13.0 meters. Solve that there, we get 390 joules. Nothing funny going on there, just basically understanding what our work is. One force makes an object move a certain distance. 2. A 50 Newton force is applied at an angle of 27 degrees above the horizontal in order to move a cart 22 meters. How much work was done? Okay, so we're pulling at some angle here. Now we know in this case, that's a case where you got to use the slightly more advanced equation involving work, FD cosine of theta. This has to be the angle between the force, this is where our force is going, and that's where our displacement's going, and that's always going to be that angle. So all that does is just gives you the component of force in the direction of motion. So 50 newtons times our distance, 22.0, times cosine of 27. Plug in our numbers there, we get 980 joules. Can friction do positive work? Very simple answer there, and that is no. Friction can only do negative work. Okay, as an object slides across the floor, got our object, and the floor here. Okay, if an object's moving this way, meaning that's the direction its displacement's going, friction has to be this way. It takes you away from that. It's in opposite directions. So that's the first reason. And second reason is, if you remember, that work is always equal to a change in kinetic energy. Friction can never increase the kinetic energy of an object. It can only take it away. So it has to be negative. Friction, work done by friction, is always negative because it's always taking away kinetic energy from that object. Moving right along, number 4. A little bit longer one. 100 kilogram object is moving at a speed of 8 meters per second. So we have a mass there. We have speed. Friction then causes it to slow down and come to a stop. How much work was then done on it? Okay, so we'll call this a V initial, and since it's coming to a stop, that means that V final is equal to 0. Okay, again, like we said in the last slide, friction is taking away energy. How much work was done on it? Since we lost kinetic energy, that work is equal to a change in kinetic energy. That's what we call the work-energy theorem. Anytime we do a change in it, it's KE final minus KE initial. Final value minus initial value. Okay, our final kinetic energy is 0. So right away there, we can see our answer is going to wind up being negative. So our work is equal to negative KE initial, which is just going to be 1/2 mv initial squared. So 1/2 times our mass times our VI, which is 8. Don't forget to square that. And this gives us 3,200 joules of work being done. Now these last two questions says what is the force of kinetic friction and what is the coefficient of kinetic friction between the car and the road. And that's all if it occurred over a distance of 17 meters. This section here, I wouldn't really worry about for the test since we haven't covered that much, but I will answer it. It's really not that hard. Since this is the work done, that work is also has to be equal to F times D. Since friction is the thing that's doing the work, that's the force. This is the force of kinetic friction there. So in order to get the force of kinetic friction, all we have to do is take the work that was done and divide it by the distance that it acted over, 17 meters. and we get 188 newtons. That would be our force of friction. Again, I wouldn't really worry about that one so much for the test. And then for the last one, it just asks what the coefficient of friction is. In which case, you just use this equation, μk Fn, to solve for μk. Just remember that Fn is always equal to mg. So if μk mg, you know what m is, you know what g is, you have k, fk, solve for μk. When you do that, it comes out to be 0.19. Again, for the test though, I would mostly just worry about this part of question 4. Number 5. An object has 700 joules of kinetic energy. If its speed is then increased by a factor of 3, how much kinetic energy will it have then? Okay, remember, kinetic energy is equal to 1/2 mv squared, which means that Ke is proportional, that's what that symbol means, it's proportional to v squared. So whatever happens to v, in this case, v is increased by a factor of 3, it's 3 times greater. What happens to Ke is going to be the square of that, so it's going to be 9 times greater. So we have to use that proportionality. So our answer here is going to be 700 times 9. It got 9 times greater. So what's 700 times 9? 6,300, if I'm not mistaken. Joules of energy. So again, increased by a factor of 9. 700 times 9. Hopefully my elementary math is correct there. Moving right along. Number 6. So the stone falls from rest from the top of a 30-meter tall cliff. There's our cliff. Stone falls from it down to the ground. With what speed does it hit the ground? Conservation of mechanical energy. Ke initial plus PEG initial is equal to Ke final plus PEG final. Now, we start from rest, so that cancels out. We're going down the ground. We already talked about the instant before it's hitting the ground. It lost all of its height, so we can cancel that out. So we have mgh initial is equal to 1/2 mv final squared. We have an m on each side, so they can cancel. So we have g, which is 9.8, times 30 is equal to 1/2 v final squared. Do our math there to solve for v final. And that should come to 24.2 meters per second. When you do your algebra there, don't forget to take the square root. It should be square root of 2 parentheses times 2 times parentheses 392 minus 98. Sorry about that. There was a quick mistake I just noticed in the key that I had online for you guys, and that was I had 40 in there instead of 30, mostly because I was looking at the next problem. So when you actually do this math, what I had before was incorrect. You're going to wind up with 30 square root of 588 and 24. Oh, that is what I wrote before. I apologize. 24.2. I just had the wrong number in here, I guess, then. Okay, so 24.2, if that is what I wrote a moment ago, that will be our final answer. Okay, so we have that one, 24.2 meters per second. Moving along to the next problem. And again, that one was written in error in your answer key, so that is the correct answer there. On number 7, it says a 15-kilogram stone falls from rest on the top of a 40-meter tall cliff. What speed does it have when it is 10 meters above the ground? Now, coincidentally enough, kind of the same problem as the last time, okay, except we're starting from 40 meters up. But we're only falling down to 10 meters, from 40 meters to 10 meters. So again, conservation of mechanical energy. We've done this enough time to start skipping some steps now. So we have gravitational potential energy to begin with. So we have mg, h initial. You have 0 kinetic energy. So that's what that is. Then your final kinetic energy. We will have some final kinetic energy plus your final potential energy, mg, h final. Okay, masses cancel out. There you have the mass in here too, 1/2 mv final squared. That mass cancels out. So we're left with g, h initial is equal to 1/2 v final squared plus g times h final. 9.8 times 40 is equal to 1/2 v final squared plus 9.8 times h final, which is now 10. Solving that for v final, funny thing happens, we wind up getting the same answer as we did for the previous problem, 24.2 meters per second. And that happens because it fell the same distance, okay? We want to know the final speed there. It fell the same distance as the last problem, except for it didn't get to the ground, and we had some potential energy left. So if you recognize that, that would have made a really easy answer for you on number 7. 8. Explain how the electrical energy we use in our homes and businesses can be traced all the way back to the sun. So, we have the sun here. Sun rains all over little old Earth. There's Earth for you. Okay? Hits Earth. Makes plants. There's a plant with some leaves. Okay? Those plants die. Go into the ground. They are there with other fossils. And whatever. They get pressed under layers and layers and layers and layers of Earth, turned into coal and other fossil fuels. So that energy from the sun is stored in that coal from the plants through the process of photosynthesis into coal. We burn that coal, release that energy. That's fire. Make that fire. We heat water. That water turns into steam, which turns a turbine. That's a turbine, not another sun, which is a magnet around a copper coal, makes electricity. So basically, for this answer, just explain that we burn fossil fuels, which get their energy from the sun, because fossil fuels are made from old plants and organic materials. That energy from the sun is stored in there. 9. A 1,000 kilogram car accelerates from 8 meters per second to 20 meters per second. How much work was done on the car? Work is equal to a change in kinetic energy. There's KE final minus KE initial. Okay? Anytime we're seeing the speed changes as for work, that's what you have to do. Except for here, that doesn't cancel out. So work is equal to 1/2. KE final is going to be 1/2 mv final squared minus 1/2 mv initial squared. Can't cancel out the masses there because there's no mass over here. So we get 1,000, 1/2 times 1,000 times the final squared, which is 20 squared, minus 1/2, 1,000 times 8 squared. Do our math there, plug everything in. Should get 168,000 joules. Total amount of work done. We used work energy theorem. 10. A 90 kilogram person climbed a 4.2 flight of stairs at a time of 3.4 seconds. What is this person's power? So, power is equal to work over time. When you're lifting yourself up, lifting anything up, even your own body, the work you do, or anytime you're doing work, it's force times distance. It's going to be force times distance over time. When you're lifting stuff up, you're getting higher, that means that the force you're applying is equal to that object's weight. mg is now your force. And your distance is the height that it has to go. Okay? It's the potential energy you gain, mgh, that should look familiar, is equal to work done in lifting it to that height. Now, it's only the vertical height we need, not, the distance along the steps or anything like that, because you're only doing work against gravity. You're not doing any work horizontally there. And then you divide that by time, which is 3.4 seconds. So 90 times 9.8 times height, 4.2 meters. And again, that's a height, not a distance, in a time of 3.4 seconds. Plug all that in. What do we get? We get about 190 or 1,090 watts. 11. How far must a spring with a spring constant of 85 newtons per meter be stretched to store 0.22 joules of potential energy? 0.22 joules. Okay? So potential energy in a spring, you have an equation for that, 1/2 kx squared. That'll be on your equation sheet. Anytime you're hearing something about a spring, you know you got to use that equation. So 1/2, so we have the potential energy, 0.22, is equal to 1/2 k, which is 85, times x squared. So solving that for x, it's going to be square root of 0.22 divided by, what's that, 42.5? Or not 0.45, but 45. What do you do that? 0.07 meters, or about 7 centimeters. 12. What is a more physicsy way of saying burning calories? Talk about burning calories all the time with food. Burning calories is the same thing as doing work. Doing work is a transfer of energy. When you burn calories, that's exactly what you do. Burning calories all day long, even when you're sleeping. Your body's processes still moving right along. 13. What is the gravitational potential energy of a 0.25 kilogram ball when it is 1.3 meters above the floor? Real simple one there. PE is equal to M times G times H. Mass is 0.25. G is 9.8. Height is 1.3. 3.185 joules. Real simple. True or false? The joule is a relatively small amount of energy. Yes, joules are an incredibly small amount of energy. Okay? They're even smaller than a calorie, which is really a kilocalorie. Alright? So even it's smaller than a kilocalorie. So yes, it is a very, very small amount of energy. You would have to have a ton of energy to have a significant amount of joules. I think I said that wrong. Even small amounts of energy, put it that way, even small amounts of energy would have a lot of joules. In other words, it takes about 10,000 joules to melt an ice cube. 10,000 joules, so it's a pretty small unit. Sum of kinetic and potential energy is always called mechanical energy. Mechanical energies, that's what we call that. A 12 kilogram stone is being held at rest by a person 1.5 meters off the floor. Is there work being done on the stone? No, there is not. It's not moving. You need motion. You need movement for work to be done. Is the person burning calories? Person is burning calories. They are burning calories. Okay? So they are doing work on something, just not the stone. What they're doing work on is their own body. Okay? Their muscles. There's a force being applied to their muscles over some distance. Large meteor impact is one of the most destructive things that can happen on Earth. What type of energy does a meteor have before it strikes Earth? Obviously, kinetic. It's a big thing that's moving very fast. So, kinetic energy has everything to do with motion. It's so destructive strictly because it's moving. That's why it's able to do so much work of killing all the dinosaurs or destroying huge sections of land. What energy conversion allows a person to run? Okay, so it's turning into kinetic energy, energy of motion, and where is that energy coming from? That's coming from the energy in food. We didn't talk about it much, but the chemical energy, chemical potential energy in food is turning into kinetic energy. talked about how food is energy. Obviously, that's the type of energy that food energy is. How can hydroelectric energy be traced all the way back to the sun? Kind of the same things we were talking about before with coal. Okay? Hydroelectric energy is the energy of moving water, whether it be a river or a dam. That has energy because it's moving. And with the dam, they put that big wall up, with the water behind it, and then they allow the water to fall through tubes, turn a turbine, spill back over this way. So they're turning that potential energy of water into kinetic energy, which turns the turbine, which generates electricity. So where did that energy come from? It's water flowing downhill. Water flowing downhill, again, turning potential into kinetic. How did it get so far uphill? Rain and snow. How did water get up in the sky? Sun. That energy from the sun that evaporated all the water, got up in the sky, fell as water. Then we harnessed that potential energy that all that water had, that was given by the sun. We turned that into the river, to moving rivers, and so forth. We can turn into electrical energy. So again, it's because of evaporation and the water cycle, which is driven by the sun, that we are allowed to use, that we are able to use hydroelectric energy. This is a problem we did in class the other day. A player passed a 0.6 kilogram basketball down the court for a fast break. Ball leaves the player's hands with a speed of 8.3 meters per second and slows down to 7.10 meters per second at its highest point. Ignoring air resistance, how high above the release point is the ball when it is at its maximum height? I already have this one as another video on the website, so I'll just be very brief here, since that's already on the other page. But it's conservation of mechanical energy, KEI plus PE G initial is equal to KE final plus PEG final. Okay? Throwing it from here up to somewhere up there. We want to know how high above where it was released from that it went. Okay? So the only thing that we can cancel out is PEG initial, since it was thrown from a height of 0. Okay? So you have 1/2 mv initial squared is equal to 1/2 mv final squared plus mgh final. So that's what we're looking for. Okay? Every term has a mass on it, so we can cancel those out. No problem. The initial is 7.10. The final is 8.3. G is 9.8. So moving everything around, solving for the final height, get 0.94 meters. Again, if you need a more thorough explanation on that one, you can check out the other video from the problem chapters that we've done. Number 21, can a rubber bouncy ball bounce to a higher height than it was dropped from? Assuming it was dropped from us. Why or why not? No, it can't. Okay, conservation of energy. It starts with a certain amount of potential energy. As it falls, that potential energy is turning into kinetic energy. When it bounces, that kinetic energy has to go, it's not gaining any more energy. Okay? It can't wind up. It can't wind up back up here. It can't wind up with more energy than it started with. Okay? It's a closed system. The total amount of energy has to remain constant. This is a very basic explanation, a very basic consequence of conservation of energy. The gravitational potential energy of a 0.12 kilogram bird in a tree is 6.6 joules. What is the height above the bird above the ground? So gravitational potential energy, mgh, 0.12, 9.8. We want to solve for h, and our PE was 6.6. Solving that for h, it's 6.6 divided by 0.12 times 9.8, and 5.6 meters is our final answer there. What factors determine how much kinetic energy something has? Mass and V. Remember, V is also getting squared in that kinetic energy equation, so it's doubly important. But mass and velocity determine kinetic energy. What factors determine how much gravitational potential energy something has? Height is the big one there, as well as mass. You could also say gravity. So you'd have it'd be hard to gain a lot of potential energy on the moon because there's less gravity there. So the mass of the object, the gravity, the acceleration of gravity, and how high it is. So gravitational potential energy, whereas kinetic energy is speed, potential energy has to do with height. Okay, there's some of our more important terms in the chapter. Work. It's when a force makes an object move. Energies, the ability to do work. Kinetic energies, energy of motion. Gravitational potential energy has to do with height or position, as well as gravity. This has to do with a spring, decompressing or stretching out a spring. String stretched out, snap back in position. Power, the rate at which work is done, work done over time. Mechanical energy is the sum of all the KEs and PE. Mechanical energy is the sum of those. Conservation of energy says energy can neither be created nor destroyed. Joules is the unit for work, for every different type of energy. So all different types of energy as well as work. That's the unit for that. Watts is the unit for power. That's what that goes with. It represents joules per second. Make sure that as you're winding down your studying, make sure you look at the other problems that I've posted from this chapter, those explanations. I think everybody do really well in this test. I think we should be very well prepared. One from the early half of this chapter, the part of the chapter that was before holiday break, were some of these problems, numbers 14 and 15. We'll just do 15 really quick. I think we should probably know how to do 14 already, but let's go with 15. The coefficient of kinetic friction between a large box and the floor is 0.21. A person pushes horizontally on the box with a force of 160 newtons for a distance of 2.3 meters. The mass of the box is 72 kilograms. What is the total work done on the box? So, total work done is the sum of all the individual works. Work 1 plus work 2. There's two things doing work, okay? A person is, and friction is here. Friction and person are the two things doing work. So you're going to find the work done by the person, find the work done by friction, sum them up, and you got the total work. Okay? Now the work done by the person, we're going to have FD here and FD. That's the equation for work. Okay? So the person pushes horizontally on the box with 160 newtons of force for a distance of 2.3 meters. Okay? So that's the work done by the person. Now we're going to add the work done by friction. Okay, work done by friction, that's the frictional force. That's Fk. We don't know what Fk is, but we know how to find Fk. Remember from last chapter, Fk is equal to μk Fn. That's a normal force. And we're on a flat horizontal surface. So that means that the normal force is just going to equal the weight of the object. So this can get plugged in for Fk. μk mg. And then it's still going to be multiplied by the distance. Also remember, that force, that energy has to be, that amount of work done has to be negative because it's going the direction opposite that of the force. Okay? So the coefficient here is 0.21. The mass is 72 kilograms times 9.8, still with the distance of 2.3. Do all of our math there. 160 newtons times 2.3. So we wind up with 368 minus 340.8. 340.8. Which gives us a total work of just 27.2 joules. Joules is still talking about work. So that should take care of most of the review. We'll cover more in class as well.